Chapter 5, Section 8, the second part here, a little part just specifically about Pythagorean theorem. Not until we get to quadratic equations do we work on basically having the tool set to solve these. So I'm going to spend a little time talking about this theorem. It's used all over the place, all the way from all kinds of engineering, carpentry, all kinds of places where we can do specific measurements and determine whether our structure's following some rules that hopefully will keep the structure from falling down, right? So the Pythagorean theorem basically says that for any right triangle, if we have the lengths of the sides, and they'll define that, and if you square them and add them together, you'll get the length of the hypotenuse squared. In other words, it's a lot easier to look at it mathematically or with the diagram here. And legs are parts of the right angle right here, this A and B lengths that they're talking about. And hypotenuse is the side opposite the right angle. This little square indicates a right angle. And we use right triangles all the time in a lot of different applications. A lot of stuff in geometry. In fact, there's a whole part of mathematics usually focused in on trigonometry, which is working with triangles. So this is pretty important stuff. So, but this theorem works all the time, or they think it does. It's still a theorem, but they've never disproven this, to my knowledge, anyhow. And so we end up with this equation here that it has, we're in that degree 2 area again, so we have a way to deal with this now that we know how to solve quadratic equations. So here's Pythagorean theorems written out algebraically. You need to know what the A and the B and the C are. This is one leg, another leg, and the hypotenuse. And they can draw a picture of this here, right? And this was a theorem that was discovered, or basically discovered this pattern that happens in life and those kinds of things, real life stuff. And this is a very good diagram of what this is. If we look at squares, really, in that the term something to the 2 power is a square. Well, if I took these legs right here of this triangle and the hypotenuse, and if I drew a square basically off the length of each one of those sides of that triangle, this would represent 3 squared, right? In other words, I'd have 9 1 unit squares, and that's how area is defined, right? That's why the nickname for the 2 power is squared. Okay. Well, same thing with this leg. If I took this length 4, I can create a square out of that, which is a 4 by 4 square. I'd end up with 16 units in there. And here's the hypotenuse, the side opposite the right angle, and I'd end up with 25 units in there of area. Okay. So that's a very good picture of how this works. And they have, like I said, this tends to always work. So we can use this equation to determine the length of a third side. So if what this allows me to do, and they're just going to do one example, but if you think about this, if I know 2 sides of any right angle, it doesn't matter if they're legs and a hypotenuse, a leg and a hypotenuse, 2 legs, and I don't know the hypotenuse, and any of those. If I know 2 lengths of a right triangle, I can always find the third length. And like I said, we use right triangles all over the place. So let's look at example 5 here. It says a 50-foot diagonal brace on a bridge connects a support under the road surface at the center of the bridge to the side support of the bridge. I'm definitely hoping they draw a picture, right? The horizontal distance that it spans is 10 feet longer than the height that it reaches at the top of the bridge. Find both distances, okay? I'm definitely going to draw a picture to try to illustrate this, right? So familiarize us. That's what they say first. Make the drawing. Now, if you don't know what braces are and those kind of things, you might need to look up a picture of a bridge. But they're going to come up with this and saying, here is what they're talking about. Is this triangle right here, you might get confused. This is not a right triangle. This is an isosceles triangle. But it splits into two right triangles here. That's what we need to focus. First, I have to have a right triangle for Pythagorean's theorem to work. So I have this triangle. Now they start labeling this or familiarize us with it. What are they telling me? They're saying the diagonal brace, right? Diagonal for this rectangle is what they're talking about. This diagonal is 50 feet long. So I need to know where that is. And then they tell us the horizontal. Horizontal means distance going across, right? That it spans is 10 feet longer than the height. Right here is the height. So if I say the height is x, then this needs to be 10 feet longer than the height, or 10 feet longer than x. So this would be 10 plus x. Now I have a way to use Pythagorean's theorem and create an equation because I have something representing the legs and a number actually for the hypotenuse. So I can take, let's say this is A is this leg right here, so it'll be x squared plus this portion here, x plus 10 squared. Remember, I have to square the entire thing. It will equal the hypotenuse squared, or 50 squared. So we have to carry that out, which is basically what do I get when I square a binomial. I'd use the pattern. Hopefully you got that pattern down. It's the first term squared plus x times 10 doubled, which is 20x, plus the last term squared right here, the 10 squared. So I end up with x squared plus 20x plus 100. I get 2x squared plus 20 plus 100 equals this, and also then when I square 50 I get 2500. So now again I have a quadratic. I can't do anything until it's equal to 0. If I'm going to get factors, it doesn't matter if they're equal to some number other than 0. I can't do anything with that. There's still an infinity of multiplications to even get like 1, right? I can take 1 times 1, 1/2 times 2, and so on. I could just keep going on forever. There's an infinity. But when I have a product of 0 again, if I have the factors, I can say there's certain conditions have to happen with these factors. Is at least one of them has to be equal to 0. So they go through the process here again. So I need to get it equal to 0. I have to square it. I need to combine like terms, add negative 2500 to both sides. So now I have a quadratic equal to 0. Then I factor. Well, always look for common factors first. There's a 2 that's common, so they factor that out. And then this is, they found factors of 1200 that will add a negative 1200 that will add up to 10, right? So they do reverse FOIL probably, and those kinds of things. So, and they say, well, possibly using a calculator would do that. I could look at factors of 12 and then, I can do it. If you're good at factoring, you can find some probably ways to do it on paper as easily as using a calculator. Well, for this to be true, now I have things multiplied together equals 0, so those factors have to be equal to 0, or I can set them equal to 0 and find a solution for the equation, or for the variable, excuse me. And I get negative 40 and 30. Well, it doesn't make sense to have a negative length in this case, so 30 is going to be what? be a good time to go back and think, what is x? Well, 30 is actually the height of my triangle, which is going to be important to know. So what is the other leg? This horizontal distance here is going to be 30, right, for x. So this is 30 plus 10, or 10 more, right? So I end up with 30, 40, 50, okay? And so we can find that out. Again, this is just one example. We're going to run into a lot of this with Pythagorean theorem. If I know any two sides of a right triangle, I can always find the third using Pythagorean theorem.